So I'd like to start by thanking organizers for inviting me here. It's really great to see such a high concentration of stream activities. This is a nice place. What will you put participate? No. So, well, we have seen already all sorts of introduction. I would like to be kind of original start from nuclear physics experiments, and then explain actually what in common experiments and frustrated units have with them. And then in the end, I would like to discuss electric excitations of experiments. So this work was a lot of this work was done with my former postdoc Andriy, now moved to Hiroshima. There's here assistant professor Yaroslav Perkov and Alexis Scott from the University of New South Wales, and Alexei put PhD student here. So, Skyrmions were invented by Tony Skyrm, working on Manhattan project, and basically he didn't believe that Skyrmions are real fundamental fields of nature, so he tried to construct them out of bosons. And so he constructed variants out of pi mesons. So he took 3 pi mesons and added the fourth one, sigma field, required that the sum of the squares is 1. And this sigma field is basically vacuum. So the normal vacuum is sigma equal to 1, and then you expand around this vacuum, you get just normal lines. But inside Skyrmions, sigma is -1, so you go in the radial direction from the center to periphery, you pass through the point where sigma is 0, and there you have all this hedgehog of ionic fields. But the big step was that he suggested that the topological charge that this soliton carries should be identified with the conserved Regan number. So that's what the serial looked like actually. That there is so if n is this 4 vectors of pi field and sigma field normalized to 1, then there is a just normal term quadratic derivatives which actually describes kinetic energy of pi mesons and also their interactions, so-called nonlinear sigma model. But he, in order to stabilize this topological solitons, he added just by hands the terms of this force order in derivatives. And that theory actually described quite well properties of protons, neutrons, their interaction with ions, their interaction with themselves. So people started actually thinking of describing nuclei as Skyrmions with higher topological number. So Skyrmions topological number 2, that would be helium. Number 3, that would be either tritium or helium-3. Number 4, alpha particles, so on and so forth. That this very fancy shape, which I will comment about later. And also, people try to describe nuclear matter as a Skyrmion crystal, and we'll see how that works out also in frustrated memories. So, magnetic Skyrmion is like a smaller brother of this Skyrmion. It has everything by 1 less. So the number of fields is now 3, and these are just components of magnetization. Now, the normal vacuum would be when the magnetization is up, so that's the ferromagnetic state, but inside the experiment is down, and so then if you go from center to periphery, it rotates. And it carries the topological charge, which is just a binding number of from one dimensional sphere to another. In Skyrmions, the topological charge has a meaning of the variant number. What is the meaning in these magnetic experiments? So we know that out of this magnetization vectors and their spatial and time derivatives, we can construct effective electric and magnetic fields, and they affect dynamics of magnets and electrons passing through the Skyrmions, and they particularly exert the Lorentz force on electrons. And so, in that sense, the meaning of topological charge of Skyrmion is basically the flux of this internal magnetic field in the z direction. It's a unit flux for electrons times the topological charge. That's true for any magnetic tension. So, and that of course gives rise to all this interesting effect like the topological Hall effect, topological Maxim Hall effect, which results in the rotation of Skyrmion crystal, and so on and so forth. But now I would like to talk about the frustrated magnet. So basically the idea is that in order to stabilize Skyrmions, a system should show a tendency to non-collinear magnetic states, and whether this is the Loshinsky-Mori interaction, or it is a dipole-dipole interaction, or it can be competing Heisenberg exchange interaction like nearest neighbor ferromagnetic, next nearest neighbor anti-ferromagnetic interaction. It doesn't really matter. So, of course, many of such systems were studied in the context of multi-ferroic materials, so they show spiral and induced polarization. But most of them are useless for Skyrmions because they are typically of very low symmetry, and so wave vector can only have one direction. But then Akuba, Kawamura, and collaborators, so they consider Skyrmions on with frustrated with competing exchange interaction on triangle lattice with second nearest neighbor and third nearest neighbor, and they found these Skyrmion crystals, double blue state, and the mixture of Skyrmions and diskyrmions. So they considered similar model, we just added the anisotropy, and then we could look at the zero temperature phase diagram and study these phases in more details. So now it has to be said that the physics of this model is, depends very strongly on where you are from the Lifshitz point. So if that model actually doesn't look like an original Skyrmion model at all, like nearest neighbor ferromagnetic interaction, next nearest neighbor and diferromagnetic interaction. But if you write this exchange interaction in the long wave limit, so when the length of the modulation is much larger than the latest constant, then you can expand it from powers of gradients. And the first term is just the time exchange, so just this rho is just the spin stiffness. And in the case of just competing ferromagnetic and anti-ferromagnetic interaction, simply J1 minus 3 J2. So if J2 is larger than 1/3 of J1, then the spin stiffness is negative, meaning that the system wants to be in inhomogeneous state. Yeah, so this one can call it like strongly frustrated magnets. Yeah, but even if it turns out that even if it's if spin stiffness is negative, yeah, then you are in that regime. If spin stiffness is positive, then the ground state is actually ferromagnetic. But it turns out that still Skyrmions can be present as isolated topological defects also in this case. And that is very nice because you don't need very strong frustration in order to stabilize those defects. What you need, however, that this fourth order term, this coefficient has to be positive, but it is positive if the next nearest neighbor interaction is larger than 1/9 of the nearest neighbor interaction, which is not so difficult to arrange, in fact. But importantly, if you just take just a ferromagnetic model, then of course it will not work. So. Okay, so let's first discuss this strongly frustrated regime. Then That's the zero temperature phase diagram, magnetic field versus anisotropy. And you see if the anisotropy is negative, that's easy plane, then you have only conical spiral, but it's easy access, you have all these different phases. And the reason why the phase diagram is richer than in chiral magnets is that basically in chiral magnets, the LANL-SkyrmionWorkshop stabilizes spirals. Whereas if you have competing exchange interaction, you stabilize all kinds of homogeneous states, spirals, sinusoidal modulation. So, so this is just a vertical spiral, but for instance, this state is a vertical spiral plus two sinusoidal modulation with different wave vectors. There is also this so-called 2Q states, which actually are 3Q states, 2Q with one sinusoidal modulation. And there is a plot state where the spiral plane changes actually. But importantly, in the large part of this diagram, you see a stable Skyrmion crystal. So that's what it looks like, and it has actually more degrees of freedom than Skyrmion crystal in the ferromagnets. So these are cartoons of Skyrmion. So this dot means spins out of the plane in the center of the Skyrmion. Crosses mean that they spins are down at the periphery, and these are in-plane spins. So, in addition to topological charts, Skyrmions are described by vorticity and helicity. Vorticity is simply the winding numbers of the in-plane spins. So here they wind in the direction of, when you go along the contour, they wind in the same direction. And so vorticity is +1, here it is -1, so that also changes the size of the topological charge. So you see in the LANL-SkyrmionWorkshop systems, the way to change the topological charge of Skyrmion is to change the direction of magnetic field, but here you can also change vorticity across the same energy. In addition, there is a helicity, the angle between the spins and the radial direction. So here it is 0, here it is pi, so these are NEA Skyrmions, pi over 2 minus pi over 2. And typically in ferromagnets, only one type of helicity is allowed, but here it becomes, if you neglect very big 6-order in-plane anisotropy, it becomes really a new degree of freedom. So you can have Skyrmions with arbitrary helicity, crystals made of Skyrmions and anti-Skyrmions, and also Skyrmions with topological numbers. So, but let me now discuss actually the case of kind of under-frustrated magnets. Yeah, so where the spin stiffness is positive, and I will consider first the case of easy access anisotropy. So that's a phase diagram for a square lattice actually as a function of the second nearest neighbor and third nearest neighbor interaction. So you have, if this frustration is sufficiently large, then you have spirals either along the square axis or along the diagonals of collinear state. And then here in this red area, you have a ferromagnetic ground state. But this dashed, all this dashed area actually is the area where Skyrmions as defects in the ferromagnetic state are stable. And this is a like a phase diagram of anisotropy versus the Maxim neighbor interaction. So, depending on where you are on that diagram, Skyrmions actually can have like a square shape or a circular shape. This is topological density. This is the color here is the Z component of the Skyrmion. So now you take one Skyrmion with topological charge -1, and you add another one. Now, if the helicities of Skyrmions helicity angles differ by pi or opposite helicity, they actually attract. If they would have the same helicity, they would repel like Skyrmions and chiral magnets. But if they are opposite, they attract and they form these Skyrmions with topological number 2. Then you add another one, you get this, another one, you get Skyrmions topological number 4 and 6 and so on and so forth. So it's clear what's happening in this case. So that is actually zero field Skyrmion defects with topological charge -6. So color here is Z component. So it's -1 inside this droplet, and it's +1 here. And all topology is actually concentrated along the boundary. And that's because basically anisotropy, easy access anisotropy likes to minimize the area where the spins lie in the plane. So, but actually that is, so this is this droplet Skyrmions, and this is a distribution of the topological charge density. That's precisely what actually an analog of what people found for nuclear physics Skyrmions. So they found out that Skyrmions with larger topological numbers are actually shallow polyhedra, or like spheres, yeah, where all topological charge density is, so this field sigma is -1 inside, it's +1 outside, but topological charge density is basically concentrated on the boundary. Yeah, so it's also, you can look at this from a different point of view. Imagine now this droplet very large, has a very large radius, so you can forget about curvature. So then these Skyrmions will form this topological stripe. So your Z component changes from positive to negative, but at the same time, so spins rotate, along this stripe. And so Skyrmion in this stripe occupies well-defined interval of lengths, and this straightened Skyrmion has less energy than the single curved Skyrmion, and that's why actually they form this droplets. So now actually you can artificially design this topological stripe by making anisotropy at the edges in plane and the anisotropy inside this structure out of plane. So this actually edge states, they carry a topological number that makes them unstable. They can pass a strong current, so they emit pairs of Skyrmion and diskyrmions, like what Erin told today, but now without any impurities yet, and then the lower edge also emits diskyrmions. And in the end, what they did, they actually exchanged the topological numbers after this exchange with Skyrmions and diskyrmions. So now, if instead of easy axis you have easy plane, then this instead of Skyrmions you have Lagrange, which are also much studied by the Salomon's group. What happens is that this instead of if spins lie in plane, then as a defect you have vortex and anti-vortex, and but inside the vortex magnetization is down, and inside the anti-vortex magnetization is up. So actually, both vortex and anti-vortex have the same topological charge equal to 1 here. So if you take a lot of vortices and anti-vortices, they all actually are defects. They cost energy, but if you see what they do, they actually form the vortex and anti-vortex crystal with the square lattice. And in fact, that's also what people found in nuclear physics. So when they modeled hadron matter with crystals of Skyrmions, they found out easily. Very soon that actually the lowest energy state is a crystal of half Skyrmions rather than Skyrmions. Yeah. So let me now move to magnetoelectric properties of these magnetic defects. These Skyrmion crystals, they consist of spirals, say 3 spirals, but a spiral breaks inversion symmetry. Yeah, so if you change the positions of all spins, then you will get a spiral that rotates in the opposite direction. And therefore, if it breaks inversion symmetry, it can induce electric polarization in the simplest mechanism, so-called inverse Bolshevsky-Mori effect. The spiral induces polarization which lies in the spiral plane and is perpendicular to the wave vector. So, and the spiral then would induce polarization in the opposite direction. So all the states in this diagram, they actually consist of 1 or more spirals, and they all induce polarization. So if you go, say, in this phase diagram, somewhere here from low field to high field, and you calculate the electric polarization out of plane is here black and in plane is red, you'll find out that vertical spiral has out-of-plane polarization. Skyrmion crystal also has out-of-plane polarization. In the flow state, the spiral plane changes, so the out-of-plane polarization goes down and in plane goes up. And in these two Q states, polarization lies in plane. So now what I would like to discuss is how one can apply electric field and excite Skyrmion motion. So this is actually from Skyrmion. This is a vortex and anti-vortex, and if you apply electric field in plane, you see that this sphere starts to rotate. Yeah, it is kind of a complicated motion, but eventually it does rotate. Yeah. So actually, it's easy to understand what's going on because the vortex, in fact, or anti-vortex, is a spiral rolled into a circle. And such a spiral induces polarization locally oriented in the radial direction. So this yellow arrows are the polarization. So if you look at all these polarization vectors, you see that polarization has divergence. So that means that the vortex should have a charge inside in the core of the vortex, yeah. And then the anti-vortex should have an opposite charge. So it's a small charge, but it's a real charge. Quite often, say when one uses Coulomb-Gas description of XY model, one assigns vortices and anti-vortices charge plus minus 1, but I'm saying that there is a real electric charge in vortices and anti-vortices. And when you apply electric field in this direction, it actually gives a force in the perpendicular direction because of that, because of this topological nature of Skyrmions, and that forces this rotation. So this is actually vortex and anti-vortex crystal, and what I do, I apply electric field in the x direction, and you see that vortices and anti-vortices move in the vertical direction, so like from a square lattice to a trellis lattice or something like that. That's actually also easy to understand. So once again, so if I apply, so these are Tilly equation for the center of mass organs of Skyrmion. So if you forget about the dissipation, which actually is rather low, yeah, so and you leave only these terms, and what happens is that if you apply force in the x direction, you change the momentum, x component of momentum. But for a Skyrmion, the role of the x component, x component of momentum is actually the y coordinate of the Skyrmion. So what you do by applying field in the x direction, you start changing the y component and the other way around. Yeah. So so now so previously it's the same. Only now the color means not the topological charge density, but the z component. So you see vortices and divertices. One kind of has positive charge, another has negative charge. I apply electric field in this direction, so then the positively charged particles move against negatively charged particles. This is just plasma oscillation, but the weird thing is that by applying electric field in this direction, I excite the y component of this plasma. Yeah? So now let me discuss the coupling to electric field which is perpendicular to the plane. Yeah, so it's the same form as the coupling, but now I take the z component of the electric dipole induced by this inverse Dolshinski Moria mechanism. And if I calculate the electric dipole, z component of electric dipole of the Skyrmion, what you find out that the Skyrmion can only have electric dipole, net electric dipole in the z direction if it has vorticity plus 1. In all the other cases, somehow the net polarization is 0. And also, this net dipole of a Skyrmion is proportional to the cosine of the helicity angle. That's to say, the near Skyrmion would have like a large dipole, the Bloch Skyrmion would have no electric dipole. And so now if I so this is a Skyrmion crystal. If I apply a magnetic field in the x direction, what you see, you find out that Skyrmion starts to move in circles, and that's actually what the Skyrmions also do in the chiral magnets. But now this helicity angle becomes excited, so also spins inside the Skyrmion start rotating. But when they rotate, that leads to oscillation of the z component of electric polarization. So we can now actually perform kind of inverse effect. So now I apply that component of electric polarization, and this is a Skyrmion, this is a Skyrmion. And what happens is that Skyrmion rotates by suddenly by angle pi, and anti-Skyrmion rotates by pi over 2. In this way, actually, maybe I can go back once again. In this way, the relative angle between spins along the line connecting the Skyrmion and anti-Skyrmion remains the same. But if I now look at this pair over a longer interval of time, what I will find out that actually this pair moves as a whole. Maybe it's so now what I did, I increased the frequency of the electric field so that actually you can see how it moves. It moves very slowly, almost as slow as was my average speed from when I moved from Ferroelectric to Santa Fe. But you see that it actually moves, yeah, so it moves. And it also rotates a little bit. That is, so rotation is basically due to the dissipative process, but motion is something different. Yeah. So, and it's important that you have like different particles, Skyrmion and anti-Skyrmion, because if you take say 2 Skyrmions, then they will not, the center of mass will not move. What they will do, they will just simply rotate around the center of mass. Yeah. So, and this is all excited once again by electric field in the direction of in the component. So what I'm trying to say is that by applying oscillating electric field, if you have Skyrmion and anti-Skyrmion pair, you can actually move them. Yeah, so translationally. So let me now, yeah. So that's if you take a Skyrmion with a large topological number, yeah, and if you take a frequency, a rather low frequency of electric field, you see you excite like pentagonal deformation of this Skyrmion. Let me just go once again. And that's because the Skyrmion with topological number 6 has like 10 block lines inside here. And so actually what you can see is that, for instance, this is one block line where spins are in the, say, out of center, and another block line when they are inside. And so, so this kind of EL parts, they have polarization up and down. And so when you apply electric field, you start deforming the shape. Yeah? So like those that have polarization up, they expand. Those that have polarization down, they contract, so on and so forth. Yeah? Okay. So in fact, you can also do it. You can consider this topological stripe that I mentioned, and you can apply, say, electric field, but now with a higher frequency. So that shows like what you see. You see the topological charge density. That's what color means here. And you see you excite like motion that of magnets that run along this domain walls actually. Yeah? So on one side up, the other side down. Okay. So okay. So maybe just very briefly where you can find it. Yeah, so actually there are a number of materials. So there is like an effort in the Netherlands on finding these insulating magnets that with competing interactions that allow for Skyrmion and other topological structures. But say kind of like basic idea is illustrated by this nickel dibromide. So it's a layered material with triangular spins forming triangular lattice, and between 52 and 23 Kelvin, actually it's like interaction between layers is anti-magnetic, and so you have like A-type structure, you have magnetism. Actually, that's because you also have easy plane anisotropy, and so that might be part of the phase diagram where you can find, say, mirror excitations. Yeah, so. But if you go lower in temperature, below 23, it develops actually the incremental modulation in planes here. But again, so between the planes, the coupling is anti-ferromagnetic. Now, this is a multi-ferroic material, so in the spiral state below 23 Kelvin, the porous group observed the electric polarization. Not very big one, but still some sizable polarization. So the one problem in observing Skyrmions with this material is that that actually is easy plane and isotropy rather than easy axis. Yeah. So, but that actually was studied quite some time ago by Moore and Day. So you can substitute iron for nickel, and iron has thrown out of plane anisotropy. And if you add a few percent of iron, actually you change the average anisotropy from easy plane to easy axis. Yeah, they didn't look for Skyrmions. Yes, well, maybe they're still there. So the other problem is that anti-ferromagnetic interaction between the layers. So you see, you have to apply magnetic field to induce Skyrmions, but if it's an anti-ferromagnetic, if you like have to apply staggered magnetic field, which is difficult. Yeah. But on the other hand, if interaction between the layers is weak, then you can overcome that. Yeah. And so this compilation with Alessio shows that actually, if the interaction between the layers is like 10% of the nearest neighbor ferromagnetic interaction, Skyrmion crystal still can exist. And the way Skyrmions cope with it is that they are shifted in neighboring layers. So if Skyrmion in one layer is here, then the Skyrmion in the other layers in between those Skyrmions, so that actually they gain on the anti-ferromagnetic interaction. You can also understand it like this. So this is Skyrmion in one layer, and this is Skyrmion in the other layer. They will actually repel and they will go on top of each other. But if they are at some distance from each other, what happens is that Skyrmion in one layer induces like shadow image in the layer 2, which has the opposite helicity. And so this Skyrmion attracts to this shadow in this layer. And of course, that also happens in the first layer. So this, in fact, the force between the Skyrmions and neighboring layers is rather big because it is mediated by these shadow Skyrmions in neighboring layers. So that means that at an elevated temperature, you can maybe easily let them go apart, so you will have real three-dimensional Skyrmions. Okay, so thank you for your attention. So I showed you that you can have interest in topological detecting even big frustrated magnets, yeah, and that you can control them by applying oscillating electric field.
Thank you for a very insightful talk. Questions and comments? Yes. So you discussed this excitation with the T equation.
Mm-hmm.
I found it interesting that the momentum is coupled to the density. Is the T equation complete, or is it not coupled to?
I don't know. Of course, you can if you want to describe, for instance, these processes, yeah, and you have to write another pair of equation, yeah, for helicity and the conjugated variable, which is, for instance, that component of monetization of the Skyrmion, yeah, and then you have to solve them at the same time because the coupling, the interaction between Skyrmions and di-Skyrmion depends on the relative helicity. Yes. So we did it actually for these edge states. We did that, and that gives qualitatively the same result as for as what you get from the full simulation.
But the question is whether these two degrees of freedom are hypothesized, or whether you can move one without changing the other.
Or you mean, for instance, if you let the Skyrmion propagate, whether it will also rotate? That depends. Because if it sees any potential on the way, yeah, then it so immediately starts rotating. So that's whether it rotates when it moves in the vacuum. Yeah, we actually do observe it. Yeah, so that it does rotate. Yeah, so but very slow rate. Yeah, so it might be actually some artifact of the simulation. So because we still consider small systems and stuff like that. Yeah. And also there is of course there is also radiation. Yeah, so we should protect the radiation.
You showed this wonderful phase diagram, very
basically, so that's, I think that is, in fact, that is kind of easier than in Monte Carlo simulations, because in Monte Carlo simulations, you know, it's a mess, yeah, basically. Yeah? So you have to calculate all correlation functions, things like that. So here it is actually very simple, yeah. So you can, once you have a structure, you do the fast Fourier transform, yeah, and then you can describe it in terms of the new Fourier harmonics that appear. Yeah? So they of course change symmetry. Yeah? So that's, I mean, in terms of like changing symmetry, that is perfectly well defined.
Let me ask you two quick questions. In the magneto-electric case, you just calculate the toroidal moment because of P plus N.
Let's see. You mean the coupling to electric field?
Yeah, the toroidal moment of the skyrmion because of this polarization.
Yeah, so the low skyrmion would have a toroidal moment, yeah. But let's see. What the coupling that I took into account, yeah, was not a kind of magneto-electric coupling. It was a coupling of polarization to magnetization and its gradient. Yeah, so it's kind of the coupling that gives rise to polarization of the magnetic structure. But it's true that the skyrmion that has a toroidal moment doesn't have net polarization. Yeah, whereas skyrmion that has monopole moment, yeah, so near skyrmion, that has polarization.
One part of the topology, the polyhedral objects that you showed before, is the genus of those objects equal to the Q continuous state that you?
Genus.
I mean, you have the object.
Oh, you mean this nuclear physics experiment?
Yeah. But you had a similar picture in your case. So does the genus correspond to the Q?
What do you mean by genus in this
Genus
case?
number holds the objects.
Yeah, I mean, genus usually used to characterize the two-dimensional surfaces. Yeah, so it's like 2 minus 2 number of holes, yeah, number of holes, and then 2 times number of petals. Yeah, so but I think these are not surfaces. Yeah, so in that sense, I don't quite understand. Yeah, so okay.
Okay, maybe if there are no further questions or comments, let's conclude this talk and thank all the speakers in the afternoon. Enjoy your evening. If you need to go to your room for 10-15 minutes. No.